without slipping. And we're going to talk about this rolling along a flat surface. It doesn't have to be horizontal, but it has to be flat. And if you choose a coordinate system with the positive y-axis straight out of the surface, so we're talking about like an incline, there's the center. The coordinate system has the y-axis pointing from inside the surface to outside the surface, and that means x is that way. Then the velocity of the center is negative omega r 0, 0. And the acceleration of the center is negative alpha r 0, 0. And so what we're talking about here is we're assuming that the angular, like a positive value of the angular velocity and the angular acceleration are counterclockwise. You can think of those also as so omega and alpha are the z components of the angular velocity and angular acceleration vectors. And r is the radius of the wheel, ball, etc. Okay, so let's say that we have this thing rolling horizontally. And let's say that we have an angular velocity of 3 radians per second. And let's say that it's slowing down. So if it's slowing down, the angular acceleration is the other way. So let's say this is 10 radians per second squared. Let's say the radius of this disk is 0.5 meters. And we want to calculate the velocity and acceleration of this point P.
Is angular velocity always slowing down? I mean, always negative?
Velocity vector and acceleration vector of that point P. Okay, well, first let's calculate the angular velocity in it. No, there's no reason. Is there a reason to do that? Well, first, this is the center, okay? So for rolling without slipping, maybe the first step would be let's calculate the velocity and acceleration of the center. Why do we need to do that? Okay, we're trying to calculate the velocity and acceleration of that point P, right? And the velocity of that point P relative to the ground is the velocity of P relative to the center plus the velocity of the center relative to the ground. Okay. Yeah, right. So if this was just like the Ferris wheel and it wasn't touching the ground, and this was at rest, the center was at rest, then it would just be a circular motion problem to calculate the velocity and acceleration of that point. But as this thing's rotating, the center has a velocity and acceleration that we can get from the rolling without slipping equations. And so we're going to set it up this way, where this is circular motion of P around C, and this is rolling without slipping. And we're going to do the same thing with the acceleration. So the acceleration of P relative to the ground is equal to the acceleration of P relative to the center plus the acceleration of the center relative to the ground. Okay, so the velocity of the center relative to the ground is equal to negative omega times r, 0, 0. What's that omega value? What? Oh, so you have to be careful with the sign. Think of the right-hand rule. Negative. So we have negative 3, this negative of negative 3 times 0.5. Okay. 0, 0. And so that's positive 1.500. So that's the velocity of the center observed by the ground. Well, one negative is because that's the formula. Okay, and then the second one is the component. And then let's do the acceleration of the center relative to the ground too. So that formula is negative alpha r 0, 0. What's alpha? Positive 10, yep. So this is negative of positive 10 times 0.5, 0, 0. And so that's negative 50, 0, no, negative 5, 0, 0. And this is meters per second squared. Now we're going to calculate the velocity and acceleration of the point P relative to the center. So that's like assuming that for a second, we're going to treat it like the center is fixed and just do that circular motion calculation. So the velocity of P relative to the center, what equation are we going to use for that? For acceleration, it'll be the watermelon. For velocity, it's just omega cross r. Yep. So what's the omega vector? 0, 0, -3. Yep. Okay. Again, I mean, we sort of already figured it out. We just used it in a different form. Right-hand rule says that at the end of the page, our coordinate system for these kind of problems is always y-axis out of the surface, x-axis parallel. So z-axis is coming straight out towards us. So this is 0, 0, -3, crossed with the r vector. What's the r vector for that point P? That's the vector from the center of the circular motion to the point we care about. 0.5. Yep, exactly. No, that's it's the x component. You're doing it right with your hand, but not y. Yeah. So negative 0.500. Take the cross product, and you get 0, 1.50. And now for the acceleration, we'll use the watermelon equation. So the acceleration of P relative to C is equal to all ripe watermelons will rot. So we have the omega and the r, we just need the alpha. What's alpha as a vector? Uh, 0, 0, 10 in the positive z direction. By the way, this thing where rotational quantities are vectors perpendicular to the rotational motion, I mean, I understand why that seems weird, but that's going to come up over and over again. That's the way moments are calculated, angular velocities and accelerations. Lots of ways of measuring rotational, orientations are done that way. So don't shoot the messenger, but you're going to have to get used to it. Okay, so alpha is 0, 0, positive 10. The r vector is negative 0.5, 0, 0. And then we're adding that to 0, 0, -3, crossed with omega cross r, which we just calculated is 0, 1.50. So for that first term, we get 0, -50. For that second term, we get 4.500. And so the acceleration vector is 4.5, -50 meters per second squared. And now we can finally use that relative motion equation. So the velocity of P relative to the ground is the velocity of P relative to the center plus the velocity of the center relative to the ground The velocity of P relative to the center is 0, 1.50. The velocity of the center relative to the ground is 1.500. And so the velocity of that point P is 1.5, 1.50 meters per second. And so if there was like a light on that point of the wheel as it went around, and you're just tracking the motion of that light, at the instant that the wheel is at that far edge, at that far side, the instant that point is at the far edge of that wheel, it's moving at this angle at 45 degrees. Okay. Tangent to the path at that instant would be at 45 degrees. And then the acceleration of P relative to the ground. So acceleration of P relative to the ground is acceleration of P relative to the center plus acceleration of the center relative to the ground. Acceleration of P relative to the center is 4.5, negative 5, 0. Acceleration of the center relative to the ground is negative 500. And so add these two up, you get negative 0.5, negative 5, 0. On these rolling problems, anytime it asks you for velocity or acceleration of some point on the wheel or the ball or whatever it is, you're going to have to use relative motion. And anytime it says rolling without slipping, any of that, you're going to use those two equations for what the center is doing. Okay, that just has to be the case. The easiest rolling without slipping problem you could have would just ask you about the velocity or acceleration of the center. But most of the time it's going to ask you for velocity or acceleration of some other point, and you'll have to get it for the center and then use relative motion to find what's happening for that other point. Why would you care about this? Well, if you were starting a bicycle fender business and you were trying to figure out how you could use the least material and make the lightest possible thing that would block the most dirt coming off of your wheel, then you'd want to know what the acceleration was of all the different points on the wheel, so you'd know where the mud was most likely to be shaken loose, And with looking at it like this, you could compare those different values at the different points and say, like, okay, there's a lot of acceleration happening here. That would send mud into an area between here and here. There's not much happening here. So what if you aren't starting a bike fender business, or you're planning to, but not this year? Then is this useful? Well, the general answer is it's useful anytime you're trying to use Newton's laws, because this is all kinematics, but the connection between kinematics and kinetics is acceleration from Newton's second law. Okay, so like, no matter what else you know about the kinematics, I always think of acceleration as like the skyway, like you're trying to get to the 6th floor on the IDS, and I don't know if there's a skyway to the IDS, but and you're on the 4th floor of the eating at Crave or whatever downtown, Well, it would make more sense if you could just go straight from the 4th floor to the 4th floor of the IDS and then go up to. but you can't do that. There's only one skyway, you know? So wherever you are, you have to go down to the second floor, take the skyway, and then go up. And that's acceleration in trying to get from kinetics to kinematics and vice versa. You got to always go through acceleration. And so that's why often that's what you're going to be asked for.